Okay, we're going to talk about the ideal gas equation. Now, what is let's see what an ideal gas is. All right. So here's a container, and I've got gas in there. So here's my gas molecules, and we know that they're all going to be flying around in a random way. Now, in an ideal gas, and most gases at normal, the sort of pressures we work at are ideal gases. In ideal gas, the molecules don't attract each other. They're too far away to attract each other. All right, and another thing is the volume of the molecules is negligible compared to the volume of the container. And as long as those two things are true, then the ideal gas equation works really. And these two things, they are true as long as the pressure isn't too high. Because you can imagine if the pressure gets too high, then these gas molecules are going to start getting a lot closer to each other. That means they might start attracting each other. They're getting closer, and also the volume of them would not be negligible. So gases under very high pressure, they won't obey the ideal gas equation, but gases at normal atmospheric pressure, yeah, they do. So that's what the ideal bit means. So let's go on and talk about it now. So I just get rid of that. Right, so we need to think about pressure of a gas, the volume of a gas, and the temperature of a gas. Now, you might have done it in physics, you might not. The volume of a gas, if you increase the pressure, the volume goes down. So pressure is proportional. The higher the pressure, the smaller the volume. Okay. Also, the volume of a gas is proportional to its temperature. The hotter the temperature, the bigger the volume. And then pressure and volume. Pressure, the pressure of a gas will go up if you increase the temperature, because the molecules are flying around faster and hitting the walls with greater speeds. Right, so we can put all of these three things together to get PV is equal to N or 2. Well, let's just, before we do that, we can say really that PV is equal to a constant times by the temperature. And this constant, well, we can get rid of that. We don't use that. We use N, which is the number of moles, and we call the constant R, which is called the gas constant. So this is the form, this is the ideal gas equation. PV is equal to N RT. Right, we need to talk about so pressure and the units and so forth, which we'll do now. Right, but just first of all, let's put a box around that, and just so that's going to be pressure, that's volume. This is called the universal gas constant. We do need to be careful here. Right, units of pressure. We use pascals. Now, pascals are a Newton per meter squared, 1 Newton per meter squared. Pressure is force over area. Okay, that's what a pascal is. So you've got to be careful, it's not kilopascals, and most of the time atmospheric pressure is about 100,000 pascals, so you tend to use kilopascals, so you need to convert them into pascals. Volume, this is the most confusing of all really, because in this equation we'll see why, but volume is not measured in centimeters cubed or decimeters cubed, it's got to be measured in meters cubed, and people forget that, and that's the main reason why they get these calculations wrong. And then temperature. Temperature is not measured in degrees C, it's measured in Kelvin. And if you want to convert, well, the Kelvin scale of temperature is based on the fact that there is a temperature when all the molecules stop. Well, as you cool something down, the molecules will vibrate less and less and less, and eventually when they've got no energy, that is the lowest possible temperature, and you can't have any temperatures lower than that. And that temperature is called absolute zero, and it's equal to minus 273 degrees C. And that is equal to 0 Kelvin. So if you look at 0 degrees C, that's 273 Kelvin. One which is quite important to us, standard condition chemist, 25 degrees C, that's 298 Kelvin. So an increase of 1 Kelvin is the same as an increase of 1 degree. And if you want to convert your degree C into kelvins, you just subtract, you add 273. So degrees C to Kelvin, add 273. That's what you need to do. So we must use this kelvins for temperature, sometimes called the absolute scale. You can't use degrees C. Right, now let's have a little think about this constant R. The universal gas constant has got a value of 8.31. You don't need to remember that, they always tell you that. Joules per mole per Kelvin. So you may think this is a rather strange unit to have. Where does this joules bit come from here? Well, let's have a little look to see where it comes from. Right, we've got PV is equal to nRT. Let's rearrange that to get R. So R is equal to PV over NT. Now, the units of R must be the same as the units of this thing here. So let's think, what are the units of PV over NT? Okay, so pressure is measured in pascals. So that's pascals. Volume, we said, is measured in meters cubed. N is a number of moles, so that's mole. And temperature is measured in Kelvin. But I can simplify that a little bit because a pascal is equal to a Newton per meter squared, isn't it? So that should be capital N, newtons. So that's going to be N m minus 2m cubed over mole K. We can obviously do something to simplify those n's. So we're going to get N Newton meter over mole Kelvin. Now, if you remember, what is a Newton meter? When you put a force of 1 Newton through a distance of 1 meter, that's the definition of a joule. That's work done, isn't it? Force through, so it's a joule. So we can simplify further to joule over mole K and put it all onto one line, joules per mole per Kelvin. So that is why we have got to use this rather unusual unit of volume, the meter cubed, because to make it compatible with those units there. And let's just have a little think about a meter cubed, because there is a lot of confusion which arises in that, and people always get the conversion wrong. So let's think about a meter. What is we've got a cubic meter there. Right, so that's 1 meter in length. What is 1 meter? Well, 1 meter is equal to 100 centimeters. So that's going to be 100 centimeters there by 100 there, and depth of 100 centimeters. So what's the volume of 1 meter cubed in centimeter cubed then? It's equal to 100 centimeters times 100 times 100, which is equal to 1 million. So 1 meter cubed is equal to 1,000,000 centimeters cubed. So don't forget that. That is really important, and every year when I'm teaching this, I always say that, and then everyone does the homework and everyone forgets to use the right units for volume and gets it wrong. And if you look at all the mark schemes, it says, if you get this answer, they've used the wrong units, like take 2 marks off 3 or something, you get. So really don't forget that. And just, so just another little conversion. Okay, so we've got 10 to the 6 centimeters cubed is equal to, right, that's equal to 10 to the 3 decimeters cubed, isn't it? Because there's 1,000 centimeters cubed in a decimeter cube, which is equal to 1 meter cubed. So if you remember that, that's pretty useful as well. So if you ever have to convert decimeters into meters cubed, you have to divide by 1,000. Okay. Right, so let's just do a quick calculation using that then. Let's say we have, right, the question says, find the volume of 1 mole of CO2. It doesn't matter what the gas is, it's the mole of anything, we'll have the same volume. Right, 1 mole of CO2 at standard pressure, which is usually 101.3 kilopascals, let's say at 25 degrees C. And you told the value of R is equal to 8.31 joules per mole per Kelvin. Okay, so put our equation down. PV is equal to nRT. We need to find out V, so we're going to rearrange nRT over P. I need to get my calculator ready. I've now got my calculator, 1 minute. So let's put the numbers in. So we get N is 1 mole, 8.31. Now T is 25 degrees C, that's 273 plus 25, which is equal to 298 Kelvin, times 298. We need to convert our pascals, our kilopascals into pascals. So that's 101.3 times 10 to the 3. So put those numbers into the calculator and we get we get, 1 minute. Right, we get 0.0244 meters cubed. Let's convert that into centimeters cubed. Okay, so we times it by 1,000,000. And that gives us in centimeters cubed 24,400 centimeters cubed, or if we do that in dm cubed, it's 24.4 dm cubed. Now I wonder if that number rings a bell. This usually told it was 24, but I think you were told at GCSE one mole of any gas, of a gas, occupies 24 dm cubed. You might remember that. Okay, that's where this comes from then. We don't work out the volumes of gases like we did at GCSE. We always use the ideal gas equation, but that number probably rings a bell. Okay, so more examples on the ideal gas equation to come.